Okay, so now we're going to talk some more about electric potential, and we're going to be looking at some electric potential distributions, or rather formulas based on different kinds of charge distributions. So here are some useful electric potentials to know. In a uniform electric field, then the the potential difference, right? That's what we're talking about. The difference here, delta V, is given by negative E dot ds, because it's uniform, so it's the same everywhere here. For a point charge, V, this is not potential difference now, this is the electric potential, is kq over r. For a series of point charges, you're just adding up all the q over r's, right, multiplying by k. And for a charge distribution now, for some charge distribution, whatever it might be, a line, ring, something like that, delta V, the change in potential energy, is from one point to the next, k dq over r. So it's kind of like we're doing this, we're adding up all these things from one point to the next. All right, so let's take a look. Imagine, we're looking for some function here that'll give us a distance away. So we go from, say, like 0 being along the axis to some distance away, r here. All right, so let's take a look. Important to know, you are not going to have to reproduce these derivations. And so these are here for you if you want to read through them, but I'm not actually going to go through these in great detail, except to point out kind of a few little things here and remind you of how this works, right? Look, we're still looking at, so this is a linear charge distribution, the potential, electric potential due to a line of charge. Notice we're a perpendicular distance d away from one end of the rod. So we're using lambda, right? Lambda is q over L, dq over dx. So it's set up the same kind of way. And now r, the distance from P to whatever little piece of the line, is square root of d squared plus x squared, where x is changing. And again, we substitute things in. So dq over dr, but dq is lambda dx, r is given by this thing. And so then we have to take the integral with respect to x of this thing, and we end up with this. So it ends up being a logarithmic thing. And the way it might help you remember this is that this looks like line, right? Line, ln looks like line, and this is due to a line of charge. That's it. Okay, so now the electric potential due to, let's see, a ring of charge, and so dv dq over r, all right, we're some distance away here, let's see, where this distance r is r squared plus x squared, and so we end up with, taking that integral, we end up with this, right, that v is kq over the square root r squared plus x squared. And then we can take a look at the electric field, right? E is negative dv dx. And notice now, when we take the derivative of that, we end up with our old formula for the electric field. Before, we were calculating electric field from Gauss's law and from, adding up the electric field due to all the little charges. Now here's another way to find the electric field. I don't know if it's any simpler, but it's another way of doing that. Direction, right, if this is positive, then direction is away. If this is negative, then the direction is in towards the center of the ring. Okay, and now due to a disk of charge, something like this, let me see if I can center that a little more. There we go. And sigma is the surface charge density, same kind of way that we did this for electric field. And what we end up with is this, right, k sigma pi 2 y squared plus r squared to the 1/2 minus y. Kind of a nasty formula, but that's what we get. Right. To find the electric field, then, if we take the derivative of this formula, then we end up with this, right, which is what we had found before for a disk, the electric field due to a disk. Okay, so the electric potential due to a uniformly charged spherical insulator. Right, so it's uniform charge inside, uniform charge density. It's an insulator, meaning that the charge is distributed inside, right? It's not all sitting on the surface the way it would on a conductor. And so here, whoops, sorry, skipped ahead a bit. There we go. There we go. So E is kq over r squared, negative dV dr, and so what we're going to be doing is adding up the electric field as we get farther away. Right. So here we're not starting with V and getting to E. Here we're starting with E, and we're going to find delta V as a result. Okay, and then we set V at infinity is equal to 0, right? Because if we put 0 in for R, that's where we get 0 potential. And so the limits are from infinity to R. And we're starting at infinity and coming to R for kq over r squared. And what we end up with is that delta V is from infinity to R is kq over R. And then that's what we can kind of call absolute potential, right? It's not just a potential difference between 2 points. This is what we call just the potential due to some charge. Okay. And so this is outside the sphere. Now, on the sphere, on a spherical insulator uniform charge density, we end up with really the same thing, right? Except now it's kq over r, where r is the fixed radius of the sphere. And then if we're talking about being inside the sphere, so a point like D or something like that, then we end up with this. Right, so we're going from delta V would be Vd minus Vc, right? So we're looking at going from r to little r. We're going inside. And so we end up with this. Right? It'll be Vd minus Vc. And then doing some algebra along the way, right? All these little steps. We find out that Vd is equal to kq over 2r cubed and 3r squared minus little r squared. Okay. And so that's kind of a nasty formula. It's not very clean. Right? We like to have something that, for something like a sphere, but that's the formula we end up with. And so this is what it looks like. And we're going to take this to the board now so we can see what these graphs look like. So if we have an electric potential, all right, so here's the electric field due to a uniformly charged spherical insulator, right? So we know it looks like this, like that. This is the electric field, and that's R. This is big R here. V, though, the electric potential is going to look like this. So here's R, that's big R. This axis is the R axis. This is going to be given by 1 over R, right? It's proportional to 1 over R. But this thing in here, that was that kind of nasty formula that we had before, like this. V equals K Q over 2R cubed, and then 3R squared minus R squared. Notice, though, that if you take the derivative of this with respect to little r, then you end up with 2r here. That 2 cancels out, and you just end up with, kq over kqr over r cubed, which is the formula we had for the electric field, which gives us this. But remember now, this, or rather think this is the negative derivative of this, right? So this means that the slope is getting larger in value, but negative, right? So that means it's getting steeper in the negative direction. So this graph kind of looks like that. That's what the electric potential looks like on the inside of a uniformly charged spherical insulator. All right. Now the next slide, it says a spherical shell or conductor. Right. So if it's a conductor, then all the charge goes to the outside, just like before. So here's the electric field. So inside, right, there's nothing, and then outside, it's proportional to 1 over r squared. What is this going to be then? Right. Well, look, if this is the slope, the slope is 0. So that just means that between here and here it's a flat line. Right, and that's going to be given by this. And then outside, again, it's going to be 1 over r. What that means is there is no potential difference inside of the spherical conductor or inside the shell. You can move anywhere inside of that and not experience any force from the electric field, and so you don't have to do any work. You can think of it that way, right? Q enclosed is 0 in this whole area, and so there's 0 electric field, so there's 0 electric force. So you're not doing any, the electric field is not doing any work. It's constant electric potential everywhere inside, and that is given by KQ over R. So when you're dealing with equipotential surfaces, remember that E is negative dV dr in the direction of R. Now this next part, 2 and 3, where it's like these things, I would say hold on to these for the next section that we do, because we're going to be dealing with something else here, multivariable stuff that we have to cover. It's never shown up on an AP test that I'm aware of, but it is in the curriculum, and who knows, this might be the year that they throw it on there. The stuff that it says here in 2412, this is important to know. If we have excess charge on an isolated spherical conductor, the charge distributes itself so that the electric potential is the same on all points of the surface. Okay. The surface charge density then, as a result, right, because it's a result of R, will be higher where the radius of curvature is smaller and the surface is convex. Right? At sharp points or edges, sigma, the surface charge density, may reach very high values. Right? So that means like the sharper the point, the more charge is going to collect there. And the potential in a cavity or a conductor is the same as the potential throughout the conductor and its surface. And remember that E is perpendicular to equipotential surfaces. Okay. And then you can see we have this, the graph here, that's kind of like what we were saying before, that inside the electric field is 0, and as a result that means that the voltage is constant, but notice that the voltage is the same as it is on the surface. Right? It matches that, that value. Okay, so now let's take a look at example 1. We have 2 charged conducting spheres of radii R1 and R2. They're attached with a long wire. The distance between them is great, right, and much bigger than their radii. So we want to know the ratio of the electric field 1 to electric field 2 at the surface of those things. Right. So imagine here is a sphere with radius R1. It's got a long wire that's connected briefly to R2, right? And this is there's some distance d away from each other. The thing we know is that they're going to have the same v, right? So v1 is equal to v2. As a result, k q1 over r1 equals k q2 over r2. So now let's solve this for r2. K cancels out, so r2 is going to be equal to q2 r1 over q1. Okay. So now I want to know the ratio of the electric fields. All right. So let's see what this looks like. So E1 over E2, and we know how to calculate this on the surface. This is going to be k q1 over r1 squared over k q2 over r2 squared. K cancels out, and so I'm left with q1 over, let's see, what's on the bottom here? r1 squared q2 times r2 squared. But now I can substitute for r2, right? I've got this thing as a result, and so this is going to be q1 over q2 r1 squared, and then this whole thing, q2 r1 over q1, and this is all squared. So I'm going to come down here now See this still? That's it. Okay, so I've got R1 squared. Those things cancel out. I have a Q2 squared over Q2, so I'm left with a Q2 on top. And then down here, this is now, I have a Q1 squared and a Q1 here that cancels out with one of those. So it ends up being just this Q2 over Q1. So you can see that when, it's important to realize this, when we have two conductors that are connected with a wire, they don't end up with the same electric field. That's not the same. The thing that is the same everywhere on the surface is this. And so something with a smaller radius has a larger electric field. Okay, so in this problem, example 2, this is number 2, what we have is two concentric spherical shells, 15 centimeters and 30 centimeters. This one has positive 10 nanocoulombs, and this one is negative 15 nanocoulombs. And we want to know the electric field and the electric potential, you know, in these regions. We want to find a formula for these. And so inside, you know, part A, when we're within this one, what we care about is the electric or the voltage produced by this shell, right? Or being inside. And so, well, both of them together actually. And so remember V KQ over R, and so V total is going to be K times 10 over 0.15 plus K times negative 15 nanocoulombs over 0.3. Right. And so this, I mean, this just ends up looking like kind of like this. 10 over 0.15 plus negative 15 over 0.3. All right, and that's going to be a constant value. Notice this isn't changing at all. And so if I have a graph here, let's say this is the electric field. Since this is a conductor, right, I've got two radii here. Since this is a conductor, the electric field is 0 in here. And for V, this is that's that value, right? That thing over there. I'm going to put this down a little bit. And then for part B, now we're in between. We know that when we're outside, we have an overall negative charge, right? And so this is going to end up being like this, right? So the electric field here is caused by just the inner shell. So this is going to be positive. That's going to look like this. And then outside, the electric field is going to be caused by the overall enclosed charge, which is negative. So this one then is going to look like this. Okay, so what does that look like for the voltage then? Well, being outside, right, that's 1 over R, and it's negative, so it's going to look like this. So then inside, it's going to do something like that. It's going to go down as a result. So this inner part, let's take a look at that in terms of you know, V total. V total is going to be you know, the voltage due to this outer one is constant, right? But the voltage due to this inner one, that's changing because we're getting away from it, right? So due to this inner one, it's you know, K times 10 over R, and R is changing because we're getting some distance away. And then plus, you know, K 15 over 0.3. So this looks like K 10 over R plus 15 over 0.3. And that's going to look like this, right? It's kind of going down. It starts off positive, but goes negative. Sorry, this is going to be a negative value. And that makes sense too in terms of how we think of this as the slope, right? This is the slope of this. So notice it's negative the whole time, so it's going down, and it's getting slightly less steep. So it should be like this. Rather, it's the negative derivative, right? So this is going down, so it's a positive value there. And this is 1 over r squared. This is according to 1 over r, right? So this would be, k 10 over r plus negative 15 over r. And we end up with that type of value. All right, so 3, as you look, we've got these two, kind of like we had before, right? They're connected by a thin wire. This one is 0.02 20 millimeters. So yeah, that's like 20 centimeters. So 0.2 meters. This one's 0.02 meters. This one is 0.1 meters. All right, and they've got some charge collected on them. So we'll call this Q1, and this one's Q2. And we want to see how these charges are related to each other, because we know the force between them. Now we want to find the values of Q1 and Q2. So what do we know about them? We know, since they were connected by a wire, that their potential is going to be the same at the surface, right? So we can say V1 equals V2. It means that K Q1 over 0.02 is equal to K Q2 over 0.1. Right, we cancel out the K's here. And so what we end up with then is that Q2 is equal to Q1 0.1 over 0.02. And that's saying that Q1 is equal to, or Q2 is equal to 5 times Q1. Okay, or you could say that Q1 is equal to Q2 over 5. Right? Q1 has less charge than this one. Okay, and so now what do we know? The force is the same, so F is K Q1 Q2 over r squared. We know the distance between them, right? We know the force, and we know one of these in terms of the other. So we can say that, F r squared over K is equal to, let's do this, Q1, and then Q2 is 5Q1, so Q1 squared times 5. So now I take F r squared over 5K is Q1. And then, you're just plugging in numbers here. And when I did this, I actually calculated Q2. You should end up with that Q2 is 1.06 times 10 to the negative 5th coulombs. And I don't know what Q1 is. So I guess Q1 would just be this divided by 5. So something in the realm of 2 times 10 to the negative 6th. And we know that they're both the same. They can both be positive, both negative. We know there's a repulsive force, but we don't know if they're positive or negative. Example 4 is really just kind of plug and chug. What we're looking for here is how much work is done. And so what we want to find is the potential at 2 different points. And then we want to find the potential difference times the charge. Because ultimately what we've got is that work is Q delta V. Right. And so then if we can find delta V and we know Q, right, we have this negative charge, then we can do that. Okay, so here's the ring, and we want to know how much work must be done to move the charge on the axis of the ring from 85 centimeters from the plane of the ring. So it's 28 centimeters. We want to bring it to a place where it's 85 centimeters. Right. And so the potential due to a ring is given by KQ over the square root of r squared plus x squared, where x is your distance here on the axis away, right? So let's call this point B, and let's call this point A, and the charge. All right, so what we can do is this, just say that the work is equal to this charge, which is negative 85 nanocoulombs. What is nano? 10 to the negative ninth. You know, VB minus VA. So that's going to be KQ. The charge on the ring is 350 times 10 to the negative ninth over, let's see, and then R, the radius of the ring, you know what, square minus, and then this is point B, so it's going to be 0.85. And then KQ, that's that same Q over square root of R squared minus 0.28 squared. Okay, and you know K, you know Q, R is that 24 centimeters. And that's it. I mean, so when you do this, I don't have the number here, but setting it up, doing all this work is the key thing anyway. So I would say don't worry about the number, just worry about having set it up the correct way. So taking a look at 2411, the potential at a location due to several point charges. Remember, this is a vector, or it's not a vector. It's not a vector, so you don't have to, you know, worry about direction. You're just adding up, right? K, Q over R, all that stuff. And so as a result now, the potential of the system, the potential energy of a system, U, right? So this is actually U now. This is not a potential difference. It's potential energy. That's a key thing. Potential energy versus potential would be KQQ over R. That should look just like in gravity, right? It was GMM over R squared, or GMM over R. Same thing here. And so the total potential energy of a system is this. Right? So in other words, if you had that set up and you let it go and you let all the forces act, that would be the total kinetic energy you'd have, you know, at some later time just before the collision or later on when they're all far apart from each other. Okay, so let's take a look at 2412, this last example. Okay, so one thing, it's a little hard to see on that, but that top graph in example 2412, the top graph is in kilovolts, and the bottom graph, the electric field, is in kilovolts per meter. And so the first thing, part A, it says from the graphs find the radius. Well, the radius is 1 meter. Okay, that's not so hard to see because that's where you can see that change takes place. For part B, it says from E versus R determine the charge on the conductor or shell, because it could be a conductor or a shell, right? We don't know. And so we know that E is KQ over R squared. And we know the value of that is 9 kilovolts per meter. Right. And so we can solve here, right? So Q is 9 times 10 to the third, and then R is 1 squared, over Q, which is 9 times 10 to the ninth. And so we end up with 1 microcoulomb as the charge there. And then C, we're looking for verify V graph by calculating V at 3 meters and compare that to V versus R. So V, KQ over R, and then we can, or little r rather, because just plugging that in. Okay, so now 9 times 10 to the ninth, Q is 1 microcoulomb, R is 3 meters, and when you do that you get 3 times 10 to the third volts, and that's what you get when you plug in 3 you look like you're about at 3 times 10 to the third volts. And so reflecting on the fact that the potential difference is the same, or the potential difference is 0 everywhere inside of a shell or a conductor, that's why you're safe inside of a car. Right? You will get shocked if there is a potential difference across your body, and charge will want to flow. But if the potential difference is 0, then there won't be any flow of charge. And so that's why inside of a car, when all of the charge is around the outside, the potential is the same everywhere inside. There's no potential difference, and you're safe inside. Okay, that's it.